Welcome back to the video series on integration and differential equations. In today's video, we're going to try an application of first-order DEs. Here's the example that we're going to be working through. The rate at which a car's value decreases is proportional to the car's value. A car's value is $32,000 when the car is new and $21,000 2 years later. Find the car's value 5 years after purchase. First thing to do in a problem like this is to define the variables. So looking over the problem, let's see what's changing. The car's value will be changing and time is changing. So those are our two variables. So let's come up with some symbols. Let's let capital V be the car's value. And we'll do that in dollars. And we'll let little t represent time, and we can do that in years. So we can choose whatever units are most convenient for the problem. Now let's see if we can come up with a DE based on the question. So we're told that the rate at which a car's value decreases is proportional to the car's value. Let's just look at this first sentence here. So the rate at which a car's value decreases, or more generally, the rate at which a car's value changes, is going to be dV by dt. That's the rate of change of value with respect to time. And we're saying that's proportional to the car's value. Now this is not quite a differential equation yet because we need to get an equal sign in here. So if we've got something is proportional to something else, the way we turn that into equality is we say, well, the thing on the left side is equal to a constant times the quantity on the right side. So K here represents some constant. It's going to be some real number that we'll discover over the course of the problem. So we've made some great progress. Now we've got a differential equation. And let's continue to highlight for ourselves the fact that we've got two different variables in this problem, the v and the t, and that k is going to be a constant throughout this problem. All right, so let's think back over our methods for solving DEs, and let's think about how we would approach this particular DE. We could separate variables. So let's try that. Let's try to get all the expressions involving v over on the dv side, and we'll get all the expressions involving t over on the dt side. So I would like to multiply by dt just so we can see which side is which, and then we can see, okay, we should divide both sides by v so that we can get all the v's on the left side. Normally, it's easiest to leave the constant in place, so I would leave the k on the right side rather than bringing it over to the left side. So that looks great. Our variables are separated. Now that our variables are separated, we can integrate both sides. On the left side, we're going to integrate dv over v to get ln v. Remember, normally we'd have absolute values on the variable here, but we said that in differential equations we're going to omit the absolute values just for convenience and because the quantities v here are going to be positive. They represent the car's value, so we don't really need absolute values at this point. All right, over on the right side, we are integrating with respect to t. K is just some number, so when we integrate, we would get kt plus some constant. Let's call our constant c1. So what we have at this point is an implicit solution to our DE. We've got an equation here where v and t are tangled up, And what I would suggest we do here is try to move to an explicit solution, so meaning actually solve for v. It'll make it easier to use some of the information in the question. In order to get rid of the ln expression, we're going to say e to the left side is equal to e to the right side. So on the left, we'll now have e to the ln v, and on the right side, we'll have e to the kt plus c1. So let's see if we can simplify these two expressions. On the left side, the exponential and the ln are inverse functions, so those will cancel. We'll just get v. And on the right side, we have to be pretty careful about our algebra rules here. So when we have a sum of things in the exponent, that's going to turn into multiplication, meaning we've got multiplication of exponentials here. We've got e to the kt times e to the c1. And we could simplify this a little bit more by noticing that c1 is a constant. So this entire expression here, e to the c1, that's just a constant. And we could rename that. We could call that c, or we could call that c2. C or c2 would both be good names. You just wouldn't want to call it c1. It's not equal to c1. It's equal to some new constant. So I'm going to go with c. At this point, we can write v in a nicer way. We can say v is equal to c times e to the kt, and I'm going to put a box around that. So every time I improve the information about v, every time I improve this function here, I'm going to put a box around it. And what we're going to do over the course of the problem now is we're going to improve this function 2 more times. We're going to figure out c, and we're going to figure out k. And once we've done that, then we can answer the question. Let's see what else we're told in the problem. We're told that a car's value is $32,000 when the car is new. So let's use that piece of information here. V is $32,000 when the car is new, meaning at time 0. So let's plug those two quantities in, see what that tells us. 32,000 is equal to our unknown constant c times e to the 0. And e to the 0 is 1, so I'm just going to cross that part off. What we're figuring out here is that 32,000 is equal to c. Okay, so let's take this information and we're going to plug it into our most recent version of our function, and we're going to update our function. So now we can say v is equal to 32,000 times e to the kt. Okay, and since that's our function, I'm going to put a box around it just so we can locate it later. So it is my habit just to put boxes around the function every time we improve it. That's just really for convenience sake, and you can see that happening in our most recent step here, because we're always going to want to look back and find the most recent version of the function. So if we've highlighted it somehow with a box or a star, then it's particularly easy to find. Alright, so at this point, this is our most recently updated function, and there's one more piece of information we can use in the problem that's going to help us find k. So let's see what else we know. We're talking about a car's value here, and we're told the car's value is $21,000 2 years later, meaning 2 years after purchase. Alright, so subbing those quantities in, we'd be subbing in v equals $21,000. And remember, we're measuring time in years, so t value of 2 would be subbed in there, and where we're subbing in to our most recent version of our equation, so this version here. Right, so that tells us 21,000 is equal to 32,000 times e to the kt and t is 2. So in the exponent you could write k times 2, but that sounds kind of weird. I'm going to write 2 times k like that. Alright, so let's see if we can use this information to find k. In order to isolate the exponential, I would divide through by 32,000. Okay, and why don't we clean up the left side a little bit just by reducing that fraction. That's really 21 over 32 that we've got on the left side. So now that the exponential is isolated, meaning it's just got a nice coefficient of 1 here, we can think about applying ln to both sides. So ln of 21 over 32 is equal to ln of the right side. And ln and exponential are inverse functions, so those guys are going to cancel. When I go ln of e to the 2k, the ln and the e will cancel, and that just simplifies to 2k. So to get k completely isolated, we could say k is 1/2 of ln of 21 over 32. Great, so we've found our k value. Let's take this information and we'll plug into our most recent version of our function, which was back here. So subbing in for k, we're going to get v equals 32,000 times e to the kt. So we'll just copy down our k value, and that still has to get multiplied by t. So there we go. That is our most up-to-date version of our value function. So now we can plug in any time value, say what any time, let's say. We can plug in any time, figure out what the car's value will be, or we can specify a value and figure out at what time would the car have that value. All right, so let's look back at the problem at this point. We used the first sentence to set up the DE, so I'm going to cross that off. We used the two facts about the car's value, so that's all done. And we're now just left with the question. So we want to find the car's value 5 years after purchase. Great, so that's going to involve subbing in a t-value of 5, because remember time is measured in years in this problem. That's what we decided at the beginning. So we'll plug in a time value of 5 and we'll be left with the car's value. As usual, subbing into the most recent version of our function. So v is going to be 32,000 times e to the 1/2 ln of 21 over 32 times 5. So I could put the 5 at the back here, but since it's multiplied with everything in the exponent, maybe a little bit easier just for the sake of typing it in to multiply it on front. So we'd have 5/2 times ln of 21 over 32. Now, just for calculator purposes, I should point out that all this stuff in the exponent should be in brackets, just so that your calculator understands that everything in here belongs in the exponent. All right, so if we were to type this into our calculator, we would get our final answer, and if I just round that off to 2 sig figs, around $11,000 is the car's value after 5 years. Thanks for watching, and we'll see you in the next video.